Hello, grade 12s. Welcome back to the channel, Science Therapy, hosted by the one and only science therapist, Uabudiwa Sos Ugobela Wemmet. And without any further ado, let's look at these questions that we have here. Ah. Okay, so we have question 2 on Newton's second law, and this is an extract from a KZN 2024 prelim paper, physics paper 1. This is 2.1 says a block of mass 3 kg is connected with a light inextensible string that is hanging over a frictionless pulley to another block of mass X as shown in the diagram below. The 3 kg block placed on an inclined plane at an angle of 30 degrees to the horizontal is pulled by a constant force of 40 Newton along the incline, while the block of mass X accelerates at 0.5 meter per second squared downwards, right? So since this is a system of blocks, we know that the acceleration of block X will be the same acceleration as the 3 kg block there, and the tension experienced by the 3 kg block will be the same tension experienced by block X, because this is a system. They need to share the same acceleration and as well as the same tension, right? So let's note that. Now below the diagram, we are given that the coefficient of kinetic friction between the 3 kg block and the surface is 0.2, right? So every time we are given the coefficient of kinetic friction, we always have to note that we have to calculate the kinetic friction, because remember, we are only given the coefficient. So we need to calculate the kinetic friction by saying Fk is equals to mu k multiplied by the normal force. Okay, so now we have 2.1.1. It says state Newton's second law of motion in weight, right? So when it comes to the definition, you have to state it as it appears in your CAPS document. So do not try to be smart and write the definitions according to your understanding. You need to write them as given on the CAPS document, right? So there is our definition there. It says when a net force acts on an object of mass, the object will accelerate in the direction of the net force, where the acceleration is directly proportional to the force and inversely proportional to the mass of the object. Again, please make sure that you define it exactly as you see it there, right? Then 2.1.2 says draw a labeled free body diagram indicating all the forces acting on the 3 kg block as it moves down the inclined plane. And then we have 5 marks. Now 5 marks indicates that we must have 5 forces. So let me just draw my free body diagram just right here. So perpendicular to the surface will be our normal force. And then in that direction, we have our applied force. So let's just indicate it like that. And then we have a rope here. So this is our tension force. And then I always prefer to resolve my gravitational force into components. So I have Fg perpendicular. And then down here, I will have Fg parallel, right? And then remember, in that direction, I will also have to have the kinetic frictional force, because now we are told that the system is moving downward. So we know that the kinetic frictional force opposes the direction of the motion, right? So, okay, in indicating my forces now, this I will say this is my kinetic frictional force. This is my force applied. And then this is the normal force. This here is the tension force, and then I have Fg parallel, and this will be Fg perpendicular. Now, if you don't prefer resolving, you know what to do. So let me indicate this big dot here to indicate this block, the object. And then there we go. I have my free body diagram just like that. Now, if you don't prefer resolving, then you know that you have to just indicate your Fg like this. But remember, if you resolve, then you must not have this. If you choose not to resolve, then you don't have your Fg perpendicular and Fg parallel, then this is what you must have. This is only weight, Fg, right? But then remember, I did explain the shortcomings of not having your diagram being resolved. It is good in drawing, but then when it comes to calculations, it might be a bit of a disadvantage because you don't get to see all the forces and the components acting there, right? So it is always a best advice to resolve, because when it comes to calculation, remember, after the question that says draw a label free body diagram, the next question says calculate. So whatever that you'll be calculating will be based on the free body diagram that you have drawn. So it is always very advisable that you draw a free body diagram that will also assist you in terms of calculations, right? So, okay. Now I have my free body diagram like this, and now they say calculate X, the mass of the hanging block. Now this is a system, and we know how to deal with questions that are based on a system. I always told you, when they give you a system of blocks, they will always ask you to draw the free body diagram of one object. But because you'll also be needing the information of the other object, it is advisable that you draw also the free body diagram of the other object, right? So we'll have to draw the free body diagram of a block X. So the forces acting on block X, up there we will have tension, and then down here we'll have our gravitational force. So note again, I'm making my gravitational force longer than the tension because I understand that the block is moving downward. So that means the force of gravity is way greater than the force of tension here, right? So which is causing the block to accelerate downward. Okay, so in this case, now when I've drawn the free body diagram for this, I can now start to calculate the F net for both these blocks, right? So let me indicate for 3 kg block, this would be the calculation thereof. So we'll say F net is equals to MA. Then note that we know that the system will be accelerating down the slope. So this here becomes our positive direction, and that there becomes our negative direction. Remember, the positive direction is the direction of motion, and the negative direction is the opposite direction to the motion, right? So this is not based on your Cartesian plane in maths. This is based on which one is the direction of motion. So the direction of motion, whether it's left or right, it is always the positive direction, right? So that means here we will have tension plus Fg parallel minus, so we have to subtract all the forces in the negative direction of motion. So minus Fk minus the force applied is equals to mass times acceleration, right? But then note that these are some of the nuggets that you always have to put in your mind. For example, Fg parallel, you always have to know that it is mg sine theta, right? And then in this case, if we want our Fk, we know that Fk is equals to mu k times the normal force. But then looking at the free body diagram, so you see the advantage of having to resolve. Now I can say that my normal force is actually equal to Fg perpendicular. So that means I can say mu k, replace the normal force by mg cos theta. Why mg cos theta? Because I know that Fg perpendicular is equals to mg cos theta, right? So we are breaking down our Fk to this because we only have the coefficient. Remember, what we are given here is not the friction, it is the coefficient of kinetic friction. So okay, in solving here, I do not have tension, but then I can calculate this one by simply saying mg sine theta. So my mass is 3, and then 9.8 sine 30 degrees. And then for Fk, I will have mu k times m times g. So that will be 0.2. And then 3 times 9.8 cos 30 degrees. And then minus the force applied. So the force applied is 40. So we were given here. So minus 40 is equals to mass times acceleration. My mass is again 3, but then I'm given that the acceleration is 0.5, right? So this is 0.5. Now if I punch all this into the calculator, all of this, and then minus 40, this will be t minus 30.39 is equals to 3 times 0.5, it's 1.5. And then now my tension is equals to 1.5 plus the 30.39, which will give me 31.89 newtons. Right. So now I've found the magnitude of the tension, but then remember what I explained. In a system, the acceleration of the 3 kg block will be the same as the acceleration of the x kg block, because this is a system, they need to share the same acceleration and the same tension, right? So even the acceleration on the x kg block is 0.5 meters per second square, meaning this tension also applies to this block. Okay, so now I will indicate for x kg block, then F net is equals to MA. Now this is supposed to be what? Fg minus tension, since now this will be the positive direction and this will be the negative direction. Again, this is the positive direction because it is the positive direction of motion. The block is moving downward, therefore this is positive and this is negative. So Fg minus tension is equals to MA, and then this will become x multiplied by 9.8. Remember, we do not have the mass. Our mass is indicated as x. Then minus, remember the tension, we already got it, 31.89. And then the mass is still x, but then acceleration is 0.5. Now, when we calculate here, we will have 9.8x minus 0.5x is equals to 31.89. So simply transposed this over here and then took this one over to this side. Right. Now when we continue with our calculation, so I will continue here. And then when we continue with our calculation, we'll get 9.3x. So from subtracting here, and then is equals to 31.89. And then if we divide both sides by 9.3, we should find x, which is the mass of this block. Then dividing there, we will have 3.43 kg, rounded off to 2 decimal places, right? So that was supposed to be your solution there. And then there we go. So make sure that you note that, and then you follow through with this calculation, and then that's it. Okay. So let's proceed. So done with Newton's second law calculation. Let's now move to 2.2, which is Newton's law of universal gravitation. It says 2.2, the moon, which has the mass of 7.35 times 10 to the exponent of 22 kg, is 1.2 times 10 to the exponent of 5 kilometers, right? So note that our distance here is given in kilometers, but that we always want our distance in meters. So we always have to remember, if we have to convert kilometers to meters, we always have to multiply by 10 to the exponent of 3 multiplied by 1,000, right? So always have that in your mind, right? So obviously, if we multiply this by 10 to the exponent of 3, this should change to 1.2 times 10 to the exponent of 8, because we'll be adding the exponents here, 5 plus 3, right? Then 2.2.1 says state Newton's law of universal gravitation in words, right? So according to our CAPS document, we say Newton's law of universal gravitation states that every body in the universe attracts every other body with a gravitational force. So the body here, we are not talking about every body in terms of the person. We are talking about the celestial objects like your Earth, your Moon, and all those, right? So it can be the Earth and versus a human being. So I'm just clarifying that everybody in the universe attracts every other body with a gravitational force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Now, it is very important to note that between their centers, right? So every time we are calculating here, we must always consider that the distance is from center to center. And now we can see that here we are given from the surface of the earth to the surface of the moon, which that means this is not the desired distance. We should also consider the radius of the earth and then also consider the radius of the moon, which is what we are being asked to calculate in 2.2.2. It says calculate the radius of the moon. Okay, so let's now get to the calculation and let me show you what I mean by that. So, okay, we have obviously our formula. So this is an interaction between two celestial bodies, the Earth and the Moon. So that means the formula that will have to work is F is equals to G M1 times M2 over R squared, right? Now the F here, that's the gravitational force between the Moon and the Earth, we are given as 1.91 times 10 to the exponent of 20. So we can just substitute it there. And then G is the constant as given in your data sheet. And then mass 1, let's take it as the mass of the Earth, which again, it is given as a constant, 5.98 times 10 to the exponent of 24, right? kg. And then that's it. So all of this, the mass of the Earth is given on the data sheet. So if you can just go and look at your data sheet, you will see this. And then also the gravitational acceleration is given. And then mass of the moon, this is what is given on the statement, 7.35 times 10 to the exponent of 22. And then over the radius here represents the distance from the center of the Earth to the center of the moon. But as I've made you note here, we are only given the distance between the surface of the Earth and the surface of the moon. That means for this radius here, we'd have to add also the radius of the Earth and the radius of the moon. But then we don't have the radius of the moon. That's what we are looking for. So radius of the Earth, again, this is a constant that is given on your data sheet. It is always given as 6.38 times 10 to the exponent of 6 meters. So we're just going to substitute it here, 6.38 times 10 to the exponent of 6. And then let's add, remember, this is the whole distance we are looking for. So we have to add the 1.2 times 10 to the exponent of, but remember, this is in kilometers, we need to convert to meters. So multiply it by 10 to the exponent of 3. We will add the exponents, and this will become 1.2 times 10 to the exponent of 8 plus the radius of the moon, and then close bracket and you square that, right? So this is the square of the distance between their centers. This is what they mean, right? So at this point, you can do your maths quick. So add these ones and then cross multiply here. So basically what we will do here is just swap positions for this one, because this is similar to just having over 1. So if you want to make this the subject of the formula, your math says you can just swap positions here. Then start by adding this. This will give us 1.2638 times 10 to the exponent of 8 plus the radius of the moon, and then square. Now, swap positions, 6.67 times 10 to the exponent of negative 11 times 5.98 times 10 to the exponent of 24, and then 7.35 times 10 to the exponent of 22, and then over. So if we swap position, this will now be on the denominator here. And then to get rid of this square here, we have to square root both sides. So square root both sides. And then we are left with 1.2638 times 10 to the exponent of 8 plus rm, radius of the moon. And then all of this inside the square root will give us 3.9178. I'm just going to round off to 4 decimal places at least. Then 10 to the exponent of 8. Now to get the radius of the moon, we understand it's 3.9178 times 10 to the exponent of 8 minus the 1.2638 times 10 to the exponent of 8. And then the radius of the moon will now give us 2.65 rounded off to 2 decimal places times 10 to the exponent of 8 meters, right? So, okay, that's how you were supposed to calculate all that. And then for 5 marks. And then all of this question, your Newton's law was for 20 marks. So always note that Newton's law carry a lot of marks, though you don't have it as your part of the syllabus in grade 12. It's from grade 11. You still need to revise your grade 11 and make sure that you always bag those marks from Newton's second law. Right, but then with all that being said, guys, please press the thumbs up button if you've enjoyed the lesson and then you have found it helpful. And if you've been watching the videos and haven't subscribed yet, please hit that subscribe button. But most importantly, please share the link with your friends and classmates so that they may also find assistance. Remember, do not be selfish. We are winning as a team.